All right, I'll begin with a word of prayer once I get up here. Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you to bless our work today. Help us to just understand a little bit more about your creation, about maximizing, minimizing stuff, and how we can use calculus to understand things about functions and their behavior. And just pray that you'd again encourage these students to do their best each day, Lord, for your glory. In your name I pray, Lord Jesus. Amen. So, somebody asked me, integration today? No, we're not to integration yet. We're getting there. But today I need to talk about, let's say extreme values for f of xy or f of xyz. I suppose what we're doing could be more general than that. But in particular, let me give you the story where we're going, okay? So we want to analyze some function of 2 or 3 variables, okay? And we want to decide, and it's a real valued function, okay? And then the question is, where is it biggest? Where is it smallest? What can we maximize it? Can we minimize it, right? And there's sort of 2 kind of questions you can ask about that. The one kind of question you can ask is, we're taking a maximum and a minimum subject to some constraint, like subject to some, we're looking at the function of 2 or 3 variables on some object, perhaps a curve for a function of 2 variables, right? Where is f of xy biggest on a curve, right? That's one question we can ask. Another question we can ask is, where is a function of xyz largest on like a surface, all right? Those are 2 kinds of questions we can ask. Those are problems of what's called constrained optimization. But we can also ask a more general question, which is like, if you've got a function that's defined on, say, all of space, like all of R2 or all of R3, is there a place where it's bigger than it usually is close to that point, right? We can look for a place where it has like a local maximum or a local minimum. So we can also ask that question. So the local max, local min question, I'm not really settling today. Today I'm just focused on the constrained optimization question. And we'll talk about how to understand local maximums and local minimums in a future lecture, okay? But you have to put these 2 things together to give a coherent answer to like interesting questions, like suppose you have a function of 2 variables and you've got some like bounded region that has a solid edge, right? Then you can ask the question, where's that function maximized and minimized on that region? So to answer that question, you'd have to look at 2 things, which would be like, where could it be biggest and smallest inside the region, right? And also, where is it biggest and smallest on the edge of the region? That's where we're going. That's what we want to understand. And I will give you this preview before I get into this, which is just that for the local max and local min, it's very much like calculus 1. You remember Fermat's theorem? What did Fermat's theorem say? If there is a local max or local min, if there's a local extreme, that has to be where what? Where you're thinking of the closed set test, but that's a good one. Yeah, where the derivative 0 or undefined. So those are called critical points, and that phenomena persists till now. A place where you have a local max or min for a function of 2 or 3 variables is also going to have to be a place where now instead of the derivative, we talk about the gradient being 0 or undefined. So, but that same notion of critical points persists, but that's for not today. So today I want to talk about, let's start with just a hypothetical. Suppose you've got we call it the objective function. So our objective is to minimize or maximize this thing. So objective function f of, let's say, I'll do the 3 variable one, f of xyz, right? And we wish to, so here's the problem. I think I told you before, mathematicians are weird. They're only happy if they have problems. It's true. And our goal, find minimum or maximum of, f along constraint surface. And we'll say the constraint surface is g of xyz equals to some constant, right? I've typically used a big F for that up to this point, But you get the idea, right? It's a level surface. So I'm going to draw a picture and derive for us a necessary condition for such a thing. So, maybe the constraint surface looks like, I guess it's going to look like all my surfaces look if they're generic in 3 dimensions like this, right? Okay, so there's my surface, constraint surface. So I'm going to say that the solution set to this is S. So here's my S, right? And let us, for the sake of discussion, let us assume that there is an answer to the question. Assume that f of p, is extremal, which is just a fancy way of saying either min-max, right? For f, on S. Okay, so then here P is an element of S, all right? So let me just draw a point here, P. Okay, so you guys tell me, if I take a curve, right? If I take a curve on the surface, let's call it gamma because why not? That's what I always call it, right? So let's suppose gamma is a path from R to S, and gamma of 0, let's let it be P, just for the sake of discussion, okay? So here's a curve, gamma. So you guys tell me, if that curve is on the surface, what equation does it have to satisfy? What does it mean to say that it's a curve on the surface in this context here? How about this? G of what? G of gamma of t should be equal to what? G? Well, remember that the equation that defines the surface is right here. G of x by z equals to c. So c should be equal to c, right? Right. So that's one thing, right? Number one, we have that. Number two, if we look at h of t, right, which is equal to f of gamma of t, then h of 0, which is equal to f of p, should be, min-max for h, which is a function from R to R. Do you guys agree? Think about this. So h, I'm just defining h to be just sampling the values of the function along the curve, right? So if p is the maximum in all, from max or min from all possible directions on the surface, then surely it must also be the max and min if we just sample directions, sample points along the curve, right? If it's a maximum for all points, it's a maximum for some subselection of points as well. So I have 1 and 2. What can I do with these? Well, what have we been doing? We've been differentiating, right? So let's differentiate 1 and 2. What do we get? We get the gradient of g at gamma of t dotted with the velocity d gamma dt equals to 0. And we get, h prime of t is equal to the gradient of f of gamma of t dot d gamma dt. Now that's not the first one's automatically 0 because why? As my little brother used to say, 'cause vy. That was when he was cute. That time has passed. Let's see here. Now, so if we put t equals to 0, what do we get here? That is, after all, the interesting point. On the one hand, we have the gradient of g at the point P dotted with, let me just use the shortened notation, gamma prime of 0 equals to 0, right? Because remember, gamma of 0 is by assumption P. And what's the second? What can you guys tell me about h prime of 0? What does h prime of 0 have to be? Since h of 0 is a local max or min, remember? We just talked about it. Fermat's theorem, right? It has to be derivative 0. So we also have, at the time 0, we have h prime of 0, which is that the gradient of f at P dotted with gamma prime of 0 is equal to 0. What does this mean? Let's think about this. This means both nabla g at P and nabla f at P are perpendicular to all tangent vectors to S at P. That means that they both have to be in the normal direction, right? By the way, this derivation still makes sense in 2 dimensions. It's just the picture's less interesting. Okay, actually this picture still makes sense in higher dimensions as well. But then the equation I'm about to write gets more nuanced. But well, in higher dimensions you need more than 1g to define a surface is the thing. So let's leave that for advanced calculus or when I'm more awake. Let's stick with this. So what this means then is that the gradient of f, right, has to be equal to some scalar multiple we call lambda times the gradient of g. So this is the so-called Lagrange multiplier condition, namely that the gradient of the objective function has to be collinear with the gradient of the constraint function. This is a necessary consequence of there being an extremal point on your surface for your objective function. So if we're going to, yeah.
And that lambda, is that just any constant?
Yeah, just any constant. It's the so-called Lagrange multiplier. And of course, I'm writing it backwards, as I always do. I started writing them backwards a long time ago, and I haven't been able to stop. So technically, that's actually lambda. Just disclaimer. Okay, so let's work a problem. So what this means is we can go looking for extremal points on the edge of things, on a surface, for example. We can go looking for extreme points because they have to, assuming that the constraint function is smooth and everything is, assuming the constraint function is smooth and that we don't have a critical point for the objective function, right? These things break down when nabla f is 0, right? So we need to look at, we should be looking at points where the gradient of f is not 0. So those 2 things in mind, smooth constraint function, non-zero gradient for my objective function. If I have a local max or min, it has to be one which is coming from this equation, right? So let's look at an example. We'll make it relatively simple here. I'll look at f of x comma y equals to x, and my constraint function g of xy equals to x squared plus y squared equals to 1. So this is a stupidly simple example. You guys could solve this without my method. What's the answer? Can you tell me? You should be able to tell me the answer to this question. What's the min-max of f on this constraint? What is the constraint? So this is a circle, the unit circle. Where is x? Where is x largest? Where is x smallest?
Max is 1.
Max is 1, min is? -1, right? So you already know the answers. They're going to be here and here. Let's see how the method of Lagrange multipliers derives that, okay? So we're going to look at the gradient of f equal to lambda times the gradient of g. Gradient of f, 1, 0. Gradient of g, 2x, 2y. This gives me two equations, namely 1 is 2 lambda x, and 0 is 2 lambda y. Lambda equals to 0 is not interesting. Okay. Like lambda equals to 0 means, I don't know, like, I guess there's different ways to talk about this. I allow lambda equal to 0. If you look at through the dozens of pages of calculations, I have these posted on my website, you'll see that I do allow lambda equal to 0 in my thinking. Maybe we should, but lambda equal to 0 is tantamount to saying that there is a critical point for your objective function. See, because if lambda is equal to 0, that means the gradient of f is 0. So usually, good practice, assume lambda is not equal to 0 to find interesting points. So here, this implies y equals to 0. Technically, it either implies y equals to 0 or lambda equals to 0, but let's focus on the interesting part. Lambda equals 0. Y equal to 0. And then what? But x squared plus y squared is equal to 1. So then that gives me what? X squared is equal to 1. Which of course has solutions x equals to plus or minus 1. So what are my solutions? Hence, f of 1, 0, which of course is 1, and f of minus 1, 0 equals to minus 1. There's my max, and here's my min. As you can see, the Lagrange multiplier equation found it for us. Now, geometrically, you can understand this. Can we understand it? Let's understand this. Let's try to understand what's going on here. What are the level curves of the objective function? What are the level curves of the objective function? X equal to a constant, right? What are those?
Lines.
Those are lines, but vertical lines, right? So if you look at it, what's happening here is where what's the gradient to the circle look like? It's, radially outward, right? Radially outward. So like it's all kinds of different ways, different places, right? That was sad. But right here and right here, it's like that. Now, where does the gradient to the x point? Well, it's always x hat, right? So here and here are your nabla f's, your gradient of f. As you can see, they're collinear at the points of min-max, right? They align perfectly. And that's the only place on the circle that happens. Everywhere else it doesn't. Not an accident. We just derived that. I mean, I derived it for surfaces, but I want to start with the two-dimensional examples. It's easier to calculate, yeah. Other questions? No? Okay. There was no question. What am I talking about? Okay, so in this case, we were successful. Our Lagrange multiplier problem gave us two answers. The minimum and maximum were there to find. Wonderful. Example 2. See, I said that it's a necessary condition. The Lagrange multiplier condition is necessary, but it is not sufficient to guarantee that you're going to find a min or max. This example will illustrate that. F of xy equals to, we'll do x again because this is a really nice example. G of xy, this time we're going to go with a hyperbola. X squared minus y squared equals to 1. Let's do the Lagrange thing first. Gradient of f is lambda times the gradient of g, which in this case gives us 1, 0, is lambda times 2x minus 2y. What are my Lagrange multiplier equations? I got myself a 1 equals to 2 lambda x. I got myself a 0 equals to minus 2 lambda y. So the algebra here is again kind of the same deal. This implies x equals to 0, hooray. And once we know x is equal to 0, what's y have to be? Oh, excuse me, I'm a dummy. Does that say x equals to what is wrong with me? Well, many things, but obviously no. Good grief. Oh. Ay, ay, ay. Sorry. What does it say? Which is 0, x or y? Y, right? The second equation tells me y equals to 0. So, oh, that's the same as last time. What's wrong with me? Okay, so y equals to 0. And if y is equal to 0, we get what? X squared minus 0 squared equals to 1. So x squared is equal to, well, x is equal to, let me get to the point here, plus or minus 1, right? So allegedly, so potentially, I should say, f of 1, 0, which is 1, and f of minus 1, 0, which is minus 1, this would be what? Max. This would be min, right? But are they? Or are these solutions illusory? Like they're not they're not really solutions. And they're not min-max solutions, right? They are solutions to the Lagrange multiplier problem, sure. They do geometrically mean something, absolutely. What does the graph of a hyperbola look like here? Well, from the algebra we just did, you can see that 1 and minus 1 are on the hyperbola, right? So it's a sideways opening one. Something like this. Right? Now, what are the level curves of the objective function? They're vertical lines, right? So we just found, of course, that point and that point are the places where the gradient of the level function, these are just, x equals to 1, x equals to minus 1. Again, the gradient aligns, right, with the these guys, the gradient to the constraint function, which is, so it's almost the same picture I drew last time, right? I believe, yeah, 2x. So like gradient of g is 2x minus 2y, so that points to the right when x is positive. It points to the left when x is negative. But I ask you the question, is this actually a maximum and a minimum for x on the hyperbola? You should tell me no. Obviously not, because the hyperbola goes what? It goes on and on and on and on, right? Like a this and like a that. So there is no global minimum, and there is no global maximum for x on the hyperbola. In fact, it goes to infinity that way, it goes to minus infinity that way. See, so these are not genuine maximum or minimum points, right? For the question that we asked at the start. Do you have a question? Comment? So my question for you guys is, what's the difference between example 1 and example 2? When can we be assured that we're going to actually find solutions for the Lagrange multiplier problem? So we need some terminology. So the terminology is what's called compact. But perhaps a better term for you guys is that example 1, the curve that we're looking at is closed and bounded. So it's closed and bounded. In other words, it's got no like fuzzy edge, all right? And it's bounded. Like you can put it in a box of finite size. If that's the case, if your curve or your surface is closed and bounded, it's said to be compact, and there's a theorem of analysis which says that if you have a continuous function on a compact set, it attains its min and max values. So you saw this as the extreme value theorem in like calculus 1. There the statement is, for example, in one dimensions, the quintessential compact set is just a closed interval. So if you have a continuous image of a closed interval, you attain a min and a max value. That's why that closed set test in calculus 1 works. If you check the endpoints and you check for local extreme in the middle, there has to be a winner and a loser in terms of the min-max problem for a continuous function on a closed set. That continues to be true for compact sets, which are sort of the analog of closed intervals for higher dimensions. So a circle is compact because you can fit it inside a ball. I mean, fit it inside a disk. On the other hand, the hyperbola is very much not bounded. It goes on and on. So in that case, we are not guaranteed that the Lagrange multiplier problem is actually successful in finding a local max, a global max and min. It may not. There may not even exist a global max and min. See, the whole derivation that we did today is subject to the assumption. Is that everybody?
Yes.
Yay. Is subject to the assumption that there is a max or min defined, right? So if there's no max or min defined, well then it doesn't work, right? So shall we work another, let's work another problem. Let's work something a little bit more difficult. Unless you guys have a question.
For an unbounded G-curve, you still could possibly find it.
Oh yes, yes. The next example will illustrate this. We'll work an honest to goodness 3-dimensional problem. We're going to find the closest point. We're going to find the closest point to a plane. All right, so what, you guys, your choice. Do you want me to do this for an arbitrary plane, or do you want me to do it for a specific plane? Okay, arbitrary. Arbitrary it is. So all that means is we're going to have ABC floating around. So example 3. It's about the same trouble to do it for an arbitrary versus specific. So here it is. Let P equal to x naught, y naught, z naught be a point not on the plane ax plus by plus cz equal to aleph. There, we haven't used aleph yet. That's a constant. You didn't expect that, did you? Let's see here. So this is just a constant. Then the question is, find closest point on the plane. Now, I could have put this problem on test 1, right? Well, it would have been nasty for me to put the problem in its current form in test 1. But maybe if I gave you a specific plane and a specific point, numerically speaking, you could have worked this, right? We have methods. We find the vector, we project onto the normal, play the games with the normal and the projection, right? Then we find the shadow of the point onto the plane. We can do this. But here, we'll use calculus. So what's our objective? Our objective is to minimize this function. Now, you could do square root, but it's just smarter to minimize the square. Because do you guys like differentiating square root? I certainly don't. So I'm going to use x minus x naught squared plus y minus y naught z minus z naught squared. See, that's the distance from my plane. So here's the plane, right? Wait a minute, it's a plane. Sorry, I've just gotten so curved lately. Forgotten how to draw a plane. There we go, plane. Right? And we've got some point off the plane, say here. So the distance to this point, x, y, z on the plane, if we square it, the square of the distance is exactly this, right? Okay. So that's my objective function. What's my constraint function? Well, it's already up here, right? This is the constraint function. Here's your g. My apologies for the hideous Carolina blue. But this marker is very long-lived. I have to give it credit. Sometimes the evil prosper. What can I tell you? They will fall. They will fall. Okay, so give it time. Gradient of f, God wins in the end. Lambda, gradient of g. What's that? No? Oh. I do that too. Hopefully not in class, though. Let's see here. So, hey, when I was working at West Alabama, sometimes I come to class and I would literally it'd just be me. Like if the student came late. This is one class. I really just had one student who regularly attended. There were 4 in the class, right? But the handy thing was, he was in the rodeo, because rodeo was a big thing at University of West Alabama. Like that's like a team sport and stuff there, the rodeo. And so I could hear him coming because he had those things on the shoes or the boots. Spurs. Yeah, he had spurs. He wears spurs, so I could hear him coming. So I didn't get scared. Anyway, so there you got lambda, gradient of g. What's gradient of g? Well, ABC. That's that. So yeah, this gives us what equations? This gives us 2 times x minus x naught is equal to like a lambda. 2 times y minus y naught is equal to b lambda. 2 times z minus z naught is equal to c lambda. For the purposes of not going crazy with case-wise logic stuff, I'm going to make the assumption that a, b, and c are all not equal to 0. At least one of them has to be non-zero. Let us agree that if both a and b are 0, this problem becomes very easy. Right? If 2 of the constants are 0, it becomes very easy because it's just a coordinate plane, a parallel to the coordinate plane. So you just look at the shadow of the point onto the plane. It tells you pretty easily what the closest point is. So this is the most interesting case when they're non-zero. And the reason I want to do that is because then I can divide. Right? I can divide. And if I divide these equations, some nice things happen, right? Like, for example, we get y minus y naught over x minus x naught is equal to what? Like b over a. And we also have, like, for instance, z minus z naught over y minus y naught is equal to, like, you know, c over b. Anyway, we can solve all of these for lambda. Maybe I should just do that. Lambda is equal to what? 2x minus x naught over a, which is equal to 2y minus y naught over b, which is equal to 2z minus z naught over c. So I have these equations. What else do I have? Yeah, I also know that ax plus by plus cz is equal to chi. I regret the chi. So then, I don't know. Then I have to solve these equations, yeah? Can we solve? I mean, is there hope? These are linear equations, right? How many of them are? What are the variables here? A, B, C are given, right? We're trying to solve for x, y, z. Do we have enough equations to solve for x, y, z? Like maybe I should take this one and rewrite this more nicely. this is canceling the 2, x minus x naught times b is equal to y minus y naught times a, right? Which I can convert to bx plus ay equal to what? X naught b plus y naught a. I'm starting to regret offering you the arbitrariness. But this is good for us to do something like this on occasion. And then how about this one? Well, see, these two, the last two here, I can look at those instead as c times y minus y naught, right? Is equal to b times z minus z naught. And that would give me the equation cy minus bz is equal to cy naught minus bz. That's supposed to be a plus or a minus? Do I have a sign error there? They can't both be plus over there, right?
Bx minus ky.
Okay, yeah. So I should have a minus in this previous equation, right? And likewise for this one, minus bz naught. All right, so at this point we've solved the problem. And what do I mean by that? What are you looking at here? This is 3 equations and 3 unknowns. Think about this. A, B, C are given numbers in this problem, right? Chi is given. X naught, Y naught, Z naught given. So here, 3 equations, 3 unknowns, you can solve this. And by you, I mean Math 221 people. Yes?
Would that be negative ay as well?
Oh, did I do that?
Negative on that.
Yes. Thank you. Thank you. Well, okay, so Sam is doubting the signs. Bx. No, the bx and the x naught b should have the same sign. They have different signs on one side, so they should have the same sign if we put them on different sides. So I think that's okay. Because I have to subtract the ay to the other side to get that. So listen, if I have 20 minutes, I can solve this. But it's kind of beastly. But you can solve systems of linear equations which are symbolic. You just go through. Have you guys talked about row reduction in Math 221 for those there? You can do row reduction symbolically on this and solve it if you want. Or you could look up my formula for the inverse of a 3 by 3 matrix and use it here. But there is actually a really clean, pretty formula for all this. And I don't think we're going to get to it in the amount of time I have. Let me just cast some shade upon this example here for a second and just tell you this is absolutely not the best way to find the closest point to the plane for a given. Well, I mean, let's put some numbers and see if we can do it. Yeah. But if you look in Stewart, there's a stone cold formula for the distance from a plane to a point off the plane. There's a nice, tight, handy dandy formula in terms of the normal and the point off the plane. It simplifies down actually quite beautifully, and so deriving that formula from our current perspective might be somewhat challenging and an interesting exercise. But let's see if we can just hack through this for a specific point and a specific plane. So I'll make the plane relatively simple. X plus y plus z equals to, let's say, 10. And the point off the plane, let us do something like 6 7, 8. So first of all, whenever I make a problem up, important thing to check, does it make sense? Is this actually a point off the plane? How do you check that?
6 plus 7 plus 8 is not 10.
6 plus 7 plus 8 is not 10. Very good. Okay, good. Very good, very good. So we would be up against specifically here gradient of f equals to, well, first of all, my objective function in this case is what? F of x, y, z. So we have specifically x minus 6 squared plus y minus 7 squared plus z minus 8 squared, right? And so I take the gradient of this thing, nabla, and I get myself a 2 times x minus 6, 2 times y minus 7, 2 times z minus 8. And that's supposed to be equal to lambda times the gradient of g. The gradient of g here is 1, 1, 1. So I get, what do I get? I get lambda equals to what? So fine, I get 2 times x minus 6 is equal to lambda, 2 times y minus z is equal to lambda, 2 times z minus 8 is equal to lambda. It just happens here that I get lambda, lambda, lambda for the other side, right? So those are literally equal. So I have, you know, x minus 6 is equal to y minus z is equal to, excuse me, y minus z. Oh no, my 7 has become a z. Ah! This would happen. We knew this would all happen. You have been like, that's going to happen. And you're like, finally, the prophecy has been fulfilled. All right, so there, I'll fix it. All right, so there we go. Y minus 7. Z minus 8. Let me make my z more fancy. There we go. So we have these equations, right? And we also have x plus y plus z equals to 10. How should we solve these? I think it's a little bit easier now, right? This tells me x is equal to like y minus 1, right? These two. And what do these tell me? I can look at the first. See, I can focus on, come on, get off, you stupid thing. If I look at this equals to that, right? They're also equal. I can solve that. That gives me that x is equal to what? Z what? Z minus 2. All right. And then what is the middle equation? How can I, if I look at the middle two, what do I get? What do these two tell me? I can take those together, and that gives me a y, or let me solve it for z. Z equals to what? Y plus 1, right? So if I take that and I shove it down in here, I get x is equal to y plus 1 minus 2, which is also known as, oh, y minus 1. That's not helpful. Check that out. Like, yay, back where I started. Hooray. Okay, so let me pause for a second here, develop a strategy. Now, the smart strategy here would be to take 221 and have a coherent, systematic way to solve these equations, right? But we don't have that, so we're just ad hoc, shoving things into things and trying to find a path through the wilderness here. But we do know x plus y plus z is 10, right? And I can try to eliminate variables if I do this wisely. Like I can do what? I can get rid of x for y minus 1. So this becomes y minus 1 plus y plus z equals to 0, right? And how can I eliminate z in favor of y? Well, I've got, what's that?
Why is it 0?
Oh, this is 0, is not 0. Good question. Still in the marker. There you go. fixed it. Thank you. I was about to get really confused. So the z I can eliminate with the red equation, right? So I've got y minus 1 plus y. My z is y plus 1 equals to 10, which gives me what? 1, 2, 3y is equal to what? Oh, 10? All right, so y is equal to 10 over 3. Once you've got 1, the rest fall. X equals to what then? 10 thirds minus 1, right? Also known as 7 thirds. And z is what?
13 thirds.
How did you get that? Oh, y plus 1. Okay, so 7 thirds plus 1. Wait a minute, no, y, 10 thirds plus 1. I can't do math. 10 thirds plus 1, which, as you have pointed out, is 13 thirds. Okay, so long story short, closest point is apparently 7 thirds, 10 thirds, and 13 thirds. Now, should this problem have an answer? Now we're trying to find min-max, right? Like, generally speaking, that's our general point of order here, right? But think about this problem for a second. Is there a maximum distance for a point off the plane? Well, obviously not, right? Because you can get the point as far away as you want. Is there a minimum distance? Logically speaking, it seems like there should be, right? So, and that's it. Now, I personally think this is a miserable way to solve this problem. By far the fastest way, as far as I know, to solve this problem is to use the normal line approach, which I sadly have not emphasized before this point. Like, I usually teach that normal line example in the previous story arc of the course, and it just slipped past me, which is why it wasn't on your test. Sorry about that. So the normal line approach just says, if you look at this, right, and you've got a point off the plane, to get to the closest point, right, this point of intersection here, if this point is 6, 7, 8, what you want is you want r of t is equal to 6, 7, 8 plus t times what? You want it to be in the direction of the normal line. That gets you the closest point. What's the normal line? 1, 1, 1. See, and if you do that, that just gives you x is 6 plus t, y is 7 plus t, z is 8 plus t, and then you just take these and you shove them into the x plus y plus z equals to 10 formula, and that gives you, 6 plus 7 plus 8, which is 21, plus 3t equals to 10, which gives us t is equal to minus 11 over 3, and then if I plug in r of minus 11 over 3, I get, 6 minus 11 over 3, 7 minus 11 over 3, 8 minus 11 over 3, which is equal to what? Well, it better be equal to 7 thirds, 10 thirds, 13 thirds, otherwise I did something wrong. What's 18 minus 11? 7. 21 minus 11, 10. 24 minus 11, 13. Is that faster?
Yeah.
Oh yeah, that's faster. So that is the way to solve this problem. But the Lagrange multiplier method, this is a good example for Lagrange multipliers because it shows you the limitations of the method, but it is by far, that's not the right tool for this problem by any means. All right. But anyway, I will find a problem tomorrow where it's the right tool, and we'll look at it, okay? So I do have more to tell you about Lagrange multipliers. So even though the course planner says it's just here today.